Welcome back to Low Vision. In this section, we're going to start with telemicroscopes and we're getting a little more clinical. Let's get started. So remember in our last video session, we talked a lot about telescopes, right? And the key thing is that we wanted telescopes to come, we wanted parallel light to come in a telescope, we want parallel light to leave a telescope, right? Because what are we typically using telescopes to look at, right? Well, with my kids and I, we like to look at the stars, you look at the moon, you like to look at things very far away from you whenever you're using a telescope typically, right? Well, what about if a patient wants to look at, instead of the stars in the sky, they want to look at the stars on their TV because they have low vision, they want to use a telescope, right? So now they're looking at an object, their TV, right, that is a lot closer than infinity, right? So what are we going to have to do? Well, we talked about this on the previous example we did, right? One of the things that's going to happen is that if we don't have parallel light going into a telescope, right, well then we're not going to have parallel light coming out of a telescope unless we adjust the telescope, right? Unless we adjust the tube length of that telescope, and that allows us to be able to do that, right? Now, the other way that we'll be able to try and modify this is to say, okay, we have a telescope, but we're looking at an object that is closer than infinity, so we don't have parallel light coming into the telescope. What can we do? Well, we can put a reading cap, right, in front of the telescope, right, and that's called a telemicroscope. So what is a reading cap? Well, reading cap is essentially a plus lens, right, that is used like a handheld magnifier, right? And remember, handheld magnifiers, you have parallel light leaving a magnifier, right? And so what we can do with a telemicroscope is we have a reading cap, we put a lens in front of the telescope, right? So that what happens is we put the object we're trying to look at, right, will be the primary focal point for that plus lens in front of the telescope, that reading cap, right? So that whenever light leaves the reading cap, it'll enter the telescope parallel and leave the telescope parallel so the patient doesn't have to accommodate it all, right? Now, another option that we could do if a patient was using a telescope, right, and they're looking at their TV to try and watch TV better, right, because they have low vision, is that we could just give them some kind of add power that they would wear in their glasses, right, to be able to view that light that would be coming out divergent from the telescope, right? So kind of three main options that we've got there. So three things we can do whenever we want to use a telescope to look at something closer than infinity, right? And you guys see those in your text, right? We can adjust the tube length, right? We can have the patient wear an add, right? They can accommodate, but typically our low vision patients are going to be older patients, so technically they have to either have an add or they would accommodate, right? Or we can use a reading cap, and whenever we use a reading cap, that's called a telemicroscope, right? All right, guys, good. So let's see that all in the text, right? You guys will see those bullet points in there. You guys see reading cap, and it acts as a handheld magnifier, right? So essentially, remember that handheld magnifiers have parallel light leaving the magnifier. All right, going on to the next page, we've got a couple of equations here that we want to use for calculating the magnification with a telemicroscope, right? So we have this equation for telemicroscopes, MT, right? So magnification for a telemicroscope is going to be equal to the magnification of the reading cap times the magnification of the telescope, right? So for our magnification of our telescope, that's going to be the equations we talked about before, right, in telescopes, right? Magnification equals, and you might want to write these in again if you want to, right? Magnification equals negative the power of the ocular over the power of the objective, right? Or magnification is going to be equal to the diameter of the entrance pupil or the diameter of the exit pupil, right? Dent over dex, right? Don't forget that minus sign in front of the power of the ocular over the power of the objective, right? For the magnification of a telescope. Now, the magnification for a reading cap is going to be simply an equation we've used before as well, right? So both these equations are ones we've used before. It's going to be the handheld magnifier equation, right? Which is your UF equation, right? Remember, U is going to be the distance that you view the object without the magnifier, without the lens, right? And then F is going to be simply the power of that lens, right? The power of the lens you put in front of the telescope, right? That's going to be our reading cap power. Now, if you use a standard viewing distance of 25 centimeters, right, to figure out the power of our reading cap, that's where that M equals F over 4 comes from, right? So if you see a question where they say, okay, you're using a standard distance for your reading cap, right, then that's going to give you your F divided by 4, all right? Now, let's kind of make this a little bit more clear in our mind and go through example 5.38 to kind of show you how these equations would come up in trying to attack in a problem, right? So let's go through example 5.38. A patient is using a 4x telescope, right, with a +3 reading cap. Notice they tell you the magnification of the telescope, so you don't have to calculate that. That's one nice step in this. What is the total magnification of this telemicroscope? What reading distance will allow the patient to view the object clearly through the telescope without accommodations? Kind of how to fill in that gap, right? All right, so once you guys work example 5.38, I'll take it to the whiteboard and we'll work it together. So let's work through example 5.38 together. So the first thing is remember we talked about whenever you assume a standard working distance of 25 centimeters to figure out the magnification of a handheld magnifier, or in this case a reading cap, which is essentially the same thing, all you do is take f divided by 4, right? You take the power of that lens divided by 4. In this example, it doesn't give you a distance that you hold the material at, right? And so in that case, you're going to say, okay, whenever it gives you a reading cap value and it says what's the total magnification, you're just going to assume a standard working distance, right? So unless they give you in the problem where they say you hold the material this far away from your eye without the magnifier, right? If they don't say that, then you're going to assume the standard working distance of 25 centimeters, and you're going to be able to use f divided by 4 for your equation to calculate the magnification of that reading cap, which is essentially a handheld magnifier. So plus 3 divided by 4 gives us 0.75 magnification. And then our total magnification is just going to be our reading cap magnification times the telescope magnification is going to give us 3x is going to be the total magnification for this setup. Now, how do you stretch this concept? Well, in this example, they gave you the magnification of the telescope. So I could see a situation where they gave you a telescope that has a value for an ocular lens, a value for an objective lens, and you have to calculate that magnification for the telescope, right? So that's one thing that I would kind of be prepared for there. They could also give you the diameter of the entrance pupil, diameter of the exit pupil as a way to be able to calculate that magnification of that telescope as well. All right, guys, going on to the next question. It says, what reading distance will allow the patient to view the object clearly through the telemicroscope? And what they mean there is clearly through the telemicroscope without accommodation, right? So what is that going to be? Remember, right, for a lens to work as a handheld magnifier, right, where does the object have to be located at? Yeah, that's exactly right, guys. It has to be located at the primary focal point, right? So all this question is asking, it says what reading distance will allow. All it's saying is what is the primary focal point for the reading cap, right? So that's all you're doing, right? All you're going to do is say what's the primary focal point for that 3 diopter lens? It's 33 centimeters or 0.33 meters. So where's the location where they have to hold the material to be able to see it clearly through this setup of the telemicroscope? All they have to do is put the material 33 centimeters in front of the reading cap, and light will enter the telescope parallel, leave the telescope parallel, no accommodation necessary, patient happy. All right, guys, let's keep on going. So what are some other uses of telescopes? Well, one of them is going to be spectacle mounted telescopes, right? Whenever we attach a telescope to their glasses and have them wear those. So there's two main types here. So center fit and bioptic fit. Now, the center fit, we think of it being right in the center of their vision, so it's going to be right in their line of sight. So going to be used for continuous viewing of an object while a patient's kind of sitting and just watching something. So I think of like a concert, watching a movie, maybe watching a sporting event, something like that. Now the bioptic fit is going to be better for them if they're being mobile, they're driving, right? Because what they're going to do is they're going to have the telescope mounted on the top of their glasses, and they can use it for spotting. So they can look down, spot something, and then go back and have their normal vision through their glasses. So bioptic fit, think upper portion of the spectacles, think spotting, right? And then you got driving, traveling in airports, things like that. Now, what would we use a reverse telescope for? Right? Remember, if we reverse the telescope, it's going to minify the image, right, instead of magnify the image. It's also going to expand the field of view, right? So whenever we think of reverse telescope, think of expanding a patient's visual field, right? You guys see that in the text right there. What type of patients would we think about doing that for? Mainly, the ones in the text, the ones I would think of too, retinitis pigmentosa, advanced glaucoma would be the two main ones I would kind of think about with reversing a telescope. Remember, expanding the visual field. Very good. Now let's talk about patients that maybe have visual field problems from maybe like a stroke, glaucoma, something like that that's caused them to have a quadrantenopia or a hemianopia, like a stroke or a tumor. Maybe they've got some advanced glaucoma in one eye, not the other, and so there's some things that we want to try to help the patient out with. What are some things we can do? Well, one of those is going to be mirrors, another one's going to be prisms, right? Try and help enhance the vision that they have, right? We're not trying to give them more vision, we're trying to enhance the vision that they have, right? And so for mirrors, primarily going to be used for temporal vision loss, where you put the mirror here in the nasal portion so they can look at that and be able to view things that are going to be temporally there. So you guys will see that that's number 1 listed there. For prisms, right, really what we're trying to do with the prisms, we're trying to shift their vision away from their defects to the area where they have better vision. So remember that the eyes always follow what? The apex or the base? Yeah, the eyes always follow the apex, right? So what we want to do is we want to put the base of the prism towards the side of the defect, right? So look at that in the text. So prisms are always placed about, 4 lines down in the text there on prisms. Prisms are always placed with the base towards the side of the defect. So we have a left hemianopsia, right? So their left visual field has problem, right? What we're going to do is we're going to put base left, so that shifts their eyes to the right. being able to use their right vision that they have, trying to enhance the vision that they have. So how much does the visual field shift with prism, right? Well, you guys look in the text, you'll see that it's about 1.75 diopters of prism shifts the visual field 1 degree. Now we can simplify that down to 2 diopters of prism for 1 degree shift in the visual field, and that's what I would remember as you're moving forward studying for your boards, right? And that's right there, and you guys see that clinically we approximate 1 degree with 2 diopters of prism. All right, guys, let's move on and let's kind of move into some clinical low vision. We're going to talk about central vision loss and peripheral vision loss. Whenever I'm attacking both these, I kind of think of them in terms of a multiple response type question. So what kind of characteristics would a patient that has central vision loss display, right? So I think central vision loss, we're going to think the cones are affected, macular disease. So what are they going to have trouble with? Well, they're going to have trouble like reading, looking at somebody's face, looking at their watch. They're going to have trouble with contrast. They're going to have trouble with color vision, right? So there's going to be some things listed here that you guys see. They're going to not have trouble with mobility, right? So patients that have a macular hole or macular degeneration, right? They're going to have trouble with their center vision, right? But their periphery is still really good. So they can still get around pretty well, but it's just things in the center where they have struggles, right? Comparing that to peripheral vision loss, that's their biggest complaint, right? We think of peripheral vision loss patients, we think of mobility issues, right? Advanced glaucoma, maybe advanced retinitis pigmentosa, maybe retinal attachment, something like that cause peripheral vision loss. That's going to be mobility is going to be the key thing that we're going to think about. All right, guys, moving on into classifying vision. We're going to talk about normal vision, near normal, and moderate low vision. I'm going to go down to moderate low vision. So 20/70 to 21/60 is where that kind of range is. Remember with these patients, they're going to have to hold things closer to them, right? To try to get some relative distance magnification, right? By holding the material closer to them. It's going to help them out, be able to see the material a little bit easier, right? But to do that, they're also going to have to converge their eyes, right? And that can be a stress on their binocular vision system, right? And so what we're going to do with this is a lot of times with moderate low vision patients, we're going to give them some prism in their reading glasses, right? Trying to help decrease that stress on their system, right? So what kind of prism do we want to give these patients? If they're having to hold things closer than normal, right? About 25 centimeters, right, or closer, right? What kind of prism are we going to give? We're going to give base in prism or base out prism? Yeah, it's going to be base in prism, right? Because what we want to do is we want to shift the image to let them be in more of a natural position, right? If we gave them base out prism, they'd have to converge more to be able to see that material. That would make things worse, right? So we want to do base in prism, right? So you guys will see that in the text. You guys will see the first bullet point there. Read usually at a distance of 25 centimeters or less to see one imprint. We'll talk about M in just a minute. You also, that's a stress of the binocular viewing system. So we oftentimes give them base in prism. You guys will see that. You want to circle that, highlight that in your text. Now, there's also a conversion factor in terms of, okay, if we give them such like an 8 diopter reading pair of glasses, what prism would we want to give them to try to help reduce their stress problems, right? You'll see that in the box, right? So in the box, you see in general, right, we take the amount of base in prism per eye as 2 plus D, which D is the spherical power of the lens. So if we were doing a 8 diopter lens, right, or 8 diopter reading pair of glasses, right, what we would do is we would do 8 plus 2, which would be 10 diopters of base in prism, and we would put that in each eye, right? So 10 diopters of base in prism per eye, so it would be a total of 20 base in total, right, for their eyes. That would be able to shift their eyes, help them out with their reading. All right, so severe low vision is to be 2200 to 2400. Now, these patients, I think the important thing to remember about these patients is they have to hold things so close, right, that binocular viewing is really not possible, right? So these patients are monocularly viewing reading material, right? So that's the key thing about severe low vision. Think monocular viewing reading material because it has to be so close. They have to close an eye to be able to make it easier for them to be able to see it. All right, so monocular viewing there. Now, 2 rules for legal blindness that you also need to know, and those are here in the text as well. Patient cannot read any letters on a 2100, right? So they have worse than 2100 vision, right? So worse than 2100 vision, that's the number 1 rule. And then number 2 is going to be a visual field diameter of 20 degrees or less, right? So 20 degrees or less in the better seeing eye. So those are 2 rules I would know, highlight those, star those for 2 rules for legal blindness in the United States. All right, guys, let's continue on and talking about M notation and visual acuity and M notation here in clinic, continuing to be clinical here. So whenever we talk about M notation, right, remember that in your text, you guys will see that the M unit, right, a 1 M letter, right, is designed by one or one that's defined. That's what I was looking for. Sorry. So 1 M letter is defined by a letter that has a size at 1 meter, right, of 1 arc minute of detail and 5 total arc minutes of size, right? So you have to set in the text. So 1M is defined as a size of a letter that has a total of 5 arc minutes of size, detail of 1 arc minute, at 1 meter, right? So let's go to the whiteboard. I want to draw a picture to kind of illustrate this point and also show you how you can convert from M notation to Snellen acuity. So whenever we look at a 1M letter at 1 meter, right, it has a total size of 5 arc minutes. So I drew an E, we got an E up here on the screen to kind of help illustrate this point. So total 5 arc minutes in size. It's got a detail of 1 arc minute. So that's going to be the MAR, right? The minimal angle of resolution would be 1. So each one of these individual bars on the E has 1 arc minute of detail for us to be able to see. Now, what's also important, right? What's also important for you guys to remember is that a 1M letter, right, at 1 meter is equivalent to 2020, right? So that would be the same size. So at 1 meter, right, the distance over the letter size, the 1M, is equal to, at 20 feet, a 20 letter size, right? And you guys have said in your text, right, this is equivalent to a Snellen acuity of 2020, right? And then in linear terms of size, a 1M letter at 1 meter is 1.45 millimeters in height, right? So 1.4 millimeters in height. So that's two things. There's some information that I would know. The big picture here, and so there's some numbers here that people tend to confuse because they try to think about 1M being 2050. So I want to show both these up there for you. So where I want to kind of simplify this for you. So at 1 meter, a 1M letter is 2020, right? Now a 1M letter at 40 centimeters or 0.4 meters, where we normally read things at, right, would be equal to a letter size of 2050 Snellen acuity, right? And you guys will see that here in the text, right? You guys see a 1M newspaper print at 40 centimeters is equivalent to 2050 Snellen acuity, right? Now, you guys will see that we can easily convert from M notation to Snellen acuity, right? Because whenever we talk about the acuity, we're talking about a distance over a letter size, right, on both sides, right? So if we have an M notation at a certain distance where you can cross multiply, right, to be able to find the Snellen acuity, right? And that's exactly what we're going to do in example 5.39. So let's go through that example together. A patient can see 2M print at a distance of 50 centimeters. What is the patient's Snellen acuity? I want you guys to work that out, and then we'll come back and work it together. All right, so to convert from M notation to Snellen, all you're going to do every time, right, is set up two fractions, right? And what you're going to do is you're just going to cross multiply to find out whatever variable you're trying to figure out, right? So we said we've got a 2M print at 50 centimeters. So we've got our 0.5 meter distance, right? Remember that acuity is always distance over the letter size, right? Test distance over letter size. So 0.5 meters over 2M letter size is going to be equal to, at 20 feet, I'll put a feet in here, right? So at 20 feet, right, what letter size, right? Now it'll give us our Snellen 20 equivalent, right? So now we're going to cross multiply and we get 80 as our answer. So that's going to be 2080 equivalent vision, right? So a 2M letter at 50 centimeters or 0.5 meters would be equivalent to a 80 size letter at 20 feet, which would be a Snellen acuity of 2080, right? So anytime we're going to try to solve a problem that's asking us to go from M notation to Snellen acuity, all we're going to do, like in example 5.39, all we're going to do is create two fractions, right? So we're going to have a test distance over a letter size is going to be equal to, at 20, so we'll put a feet in here, right? So at 20 feet, what letter size? That's going to give us our Snellen acuity equivalent, right? So remember, always test distance over letter size, right? Test distance over letter size. So 0.5 meters over 2M, you cross multiply, you're going to get 80. So that's going to be 2080 Snellen acuity, right? So it's a simple calculation. Now, where I've seen students will mess this up whenever they're doing quiz questions and working forward, right, is that they reverse these two, right? They put the letter size on bottom, right? Whenever they, and so they do like 2M over 0.5 meters equals 20 over X, right? And that'll give them a wrong answer. So just remember that it's always going to be test distance over letter size, right? Test distance over letter size. All right, guys, great job. Go dominate the quiz. I'll see you on the next video.